It's time to begin now, and I want to alert you to what's on the calendar. So right now, this homework 5, which covers chapter 7 and 8, we almost finished chapter 8 last time. We're going to finish it today and then also do 9 and probably do 10. 10's really easy. So if we don't get to it, it's not a problem. So this homework covers the end of 6, 7, and 8. And then today we'll finish 9, so I'll post that pretty soon. It's not up yet. And so you'll be able to get a good start on this homework, which will include 9, 10, and maybe some of 11. So now also you're probably wondering about this. All these pre-lectures are due Friday, but I haven't posted this bonus survey 2 yet. So to allow, I say it's due now, but since it's not posted, I'll extend it and change this calendar to say it's due Sunday. So you'll have a little more time to do this, even though it only takes a few minutes. But these have all been posted for a while, and I strongly recommend you do these pre-lectures, preferably before you listen to the lecture, because they're really easy and they'll give you a good basis to understand the lecture better. Even though they're not due till afterwards, I strongly recommend you do them, if possible, before. But if you can't get to them, that's okay. But I really recommend you do them. All right, so now let's go to the document camera and remember where we left off. We left off here on page 51, and we're talking about these statistics right here for these random variables, statistics for random variables. That means that random, they're just numbers that vary, and they vary according to some chance process. And what we've been looking at is random draws from a specified box. We've been modeling gambling games where we know what the odds are. We know what's in the, quote, population. That's our box. And we're looking at what we expect to see, our expected value in our sample. And last time we looked at the sum. So if we took, for example, we had a box like this with numbers, and we took the average of this. I think maybe these are the same. We did boxes like this, and then we said, okay, we're going to take the average of this. And if we add them all together and divide by 5, the average will be 5 here. You can probably see because it's symmetrical. And then we also looked at the standard deviation, the spread of this box. So this is like the population. So we called this average a Greek letter mu, and we called the standard deviation of it. If we were going to figure that, what would we do? We would subtract 5 from each one of these numbers, right? And we'd have negatives and positives. And if we summed them, what would they sum to? 0, right? So instead of doing that, we don't want, we'd always get 0. So we square them, then take their average, that's the variance, and then take the square root. And if we did all that, I'm not going to do it now, we get 2. And we're referring to that as sigma. Okay, so we did all that last time. And then we said, okay, if we drew from this box n times, and then took the sum of the numbers, we said we'd expect for our average to depend on the number of draws. Like if we drew 100 draws from here, we'd expect on the average to get 5 each time, 5. Sometimes we're going to get below, sometimes we're going to get above. So we said our expected value for the sum was n times the average of the box. That's what we did last time. Now, but now we're going to look at the expected value for the average of our draws. Not for the sum, but for the average. So if we drew out of here 100 times, with replacement, because there's only 5 tickets, we have to replace it, but we wrote down all those 100 numbers, and we took the average of those 100 numbers, wouldn't you expect it to be very close to the average of the box? Wouldn't you expect like an even distribution of, because we, 2s, 4s, 5s, 6, and 8s? So it would mirror our box. It would just be, we'd expect on the average to have 100 of these, 100 of those, 100 of those, 100, and 100, 500, to have an even distribution. So wouldn't you expect the average of our sample to be exactly like the average of the box? Why would you expect it to? We wouldn't get all 2s. To get an average of 2, we'd have to get all 2s. To get an average of 8, we'd have to get all 8s. We'd expect it to be 5. So it's really not going to depend on the number of draws. We really don't need a formula at all. It says the expected value of the average of the sample, no matter how big n is just going to be the average of the box. That's all. So we should write that down, same thing. So we're doing the expected value of our sample average. So the expected value of our sample average, it's going to change each time. It's going to be somewhat different depending on the luck of the draw, but we would expect it, on average, to be just the average of the box, or the average of the box, which is the same as, later we're going to be referring to it as the population, like when we take a random sample from a larger population. Okay, so that's, so we'd expect, if you wanted to use the row, another word for sample average, a shorthand for that is x bar. So we would say the expected value of x bar is mu. Okay? But right now I think it's better to just say sample average and population average so we don't have too many things to remember. All right? So I'll just leave it like that for now. Now, what's the expected value of the average of the 100 draws? We just said it. The expected value of the sample average is just 5, because it's 5 right there. All right, now we'd expect the average of the draws to be the same as the average of the box. That's just common sense. But of course the average of the draws is going to vary due to chance. And the typical variation around the average is called the standard error of the average. Okay? It's the standard error of the sample average. All right? So what is the standard error of the sample average? It's this, the standard deviation of the box divided by the square root of n. And that's called the standard error of the sample average. Okay? And so you could also say it's sigma over root n if you want. Now, doesn't it make sense, just to look at this, doesn't it make sense that the more draws you have, the more, like if you just draw, if n was just 5, we could, or like 3, let's say, we could get all 2s or all 8s, or we're going to have, it's going to vary more from the average. But if n was 300, and I took 300 times, I took the numbers from here and took the average, I'm not going to get 300 2s, right? I'm going to get closer and closer to the average of 5 the more draws. Doesn't that make sense? Wouldn't you expect if you draw from here more times, you're going to get closer and closer to your average of all those draws will be closer than the average of, look, if you just drew once or twice, you wouldn't expect to get an average of 5, right? But if you drew 1,000 times, wouldn't you expect to get an average close to 5? Of 1,000 numbers, right? The more bigger your sample is, isn't it going to get closer and closer to the, your error is going to get less and less, and your sample is going to reflect an even distribution of 2s, 4s. It's going to resemble the box distribution more and more and more, right? So you divide by. You don't multiply by the square root of n like we did before. Here's why. Maybe if you see the math will help you. Remember the standard error of the sum of n draws was the square root of n times, you multiplied here, the standard deviation of the box. This is how you, when it was this, each time you summed up another number, you got a bigger and bigger sum. Your expected value is n times the average, and then you could get further away, right? You would get further away. If you flipped a coin 100 times, you'd expect 50 heads, right? But give or take a bigger number than if you only flipped it 10 times. You'd expect 5 heads, give or take some number. But if you flip it 100 times, your error is going to grow because each time you're going to have a little bit of chance error. It's going to sum, and it sums as the square root of n, right? But now when you're taking the average, you're going to get closer by that same factor because think about what a sum is, what an average is. So to change from a sum to average, you just divide by n. So if we divide by n, it's going to simplify to that very easily. Here's our standard error for the sum, and you're going to take, here's the sum. To get an average, you're just going to divide it by n. That's how you go, that's how you take an average. So this simplifies to what? The square root of n times SD of the box over, and we'll just change that n to square root of n times square root of n. And you can see you just get that. You're dividing by n. So what I want you to remember is when you take the sum, the standard error of the sum, right here, a standard error is like a standard deviation. So they both have that, right? A standard error of the average is like a standard deviation, right? So the question is, the square root law, do you multiply or divide by the square root of n? Well, when you take the sum, you're going to multiply because your sum gets bigger and bigger and bigger, and so does your error, but not as fast. If you multiply your number of draws by n, you multiply your error by square root of n. So now when you're taking the average, right, here's the average, you're going to divide by the square root of n. So you will divide. Not multiply, but divide. Okay? So they both involve this, standard error is a standard deviation of a chance process. And your error depends on your draws. The more draws as an average, you're going to get closer. So you divide by a square root of n. But as a sum in gambling, the more times you play, the more money you could lose, and your chance error is bigger. Okay, so let's just do this example right here. It says 100 draws are made at random with replacement from this box. It's the same box as before, so the average is 5, and the standard deviation is 2. So what would you expect the average of the 100 draws to be? The expected value of the average is just of the sample average. That says average, sorry. The expected value of the sample average is just going to be your population average, right? It's just the average of the box. But what's give or take about how much? You want to put the standard error for the average in here. And we said that's what? The standard error for the average, for the sample average, is what? It's going to be the standard deviation of the box over the square root of n. That's for the sample average, right? And so what's that going to be? The standard deviation was given to you, and n is 100, so it's going to be 0.2. Okay, so let's go. Let's turn the page. And now, So now we're going to look at, so I said at the beginning we're going to look at three statistics, the sum, the average, and the percent. And we're going to look at their expected values and their standard errors. So now we've done the sum and the average. Now look at the percent. So, so the expected value of the average of n draws is just the average of the box. That's just common sense. And same with percent. The expected value of, if you're looking at a classifying into two categories, like yes and no's, and we want it, or heads and tails, and we model it with a box with ones and zeros, then the expected value of the percent of ones in the box is just going to be the expected value, what did I just say? The expected value of the percent of ones in your sample, so these are in your sample of n draws, is just going to be the same as the percent in the box. So these two, there's no formula for these. They're just common sense. If your box has half ones, wouldn't you expect your sample to have half ones? That's all we're saying. Okay, so there's no formula for the expected value for the average and the percent. It's just common sense. But now, what's the standard error of the percent? Well, what is it? Okay, it's going to be calculated the same way. I should read this to you because it will help you understand it. The expected value and the standard error for percents are calculated exactly the same way as for averages. That's because percents are just averages for 0, 1 boxes. Aren't they? They're exactly the same, just you change it to a percent. So if you take the average of a box that has 20% ones and 80% zeros, it's just going to be 0.2. And changing it to a percent is 20%. So it's exactly the same thing. So it's the same formula. So the standard error of the average is that, right? That's what your standard error of the average is. And what's the standard error of the percent? It's just going to be exactly the same thing. This would be, if you took the average of a box that had 20% ones or 30% ones and 70% zeros, then it would be 0.3. But to change it to a percent, you multiply by 100, and then it would be 30%. You know, if it was half ones, half zeros, it would be 50. It would 50% would be the expected value of it, the percent of ones. Now, to change it to a standard error, we do it exactly the same way, but then multiply it by 100. So what I mean is you do, for example, if you had a 50% ones and 50% zeros, remember the standard deviation of your box would be 0.5. So you'd say 0.5 divided by the square root of your sample size times 100. Let's do it and you'll see it. Okay? So first, let's say, suppose you draw at random from this box right here. Okay? And suppose you're just interested in the percent of twos that you get. Okay? Just the twos. So you have to change it to a 0, 1 box. So the percent of twos, so you'll say, okay, if we get a 0, that's 0 twos. If we get a 2, it's 1, 2, 1, 2. And if we get an 8, it's 0 twos. You can see right away you have 50% twos in here. So your expected value for the percent of twos, you don't have to do it to figure out this one. You have 50% twos. So expected value for the percent of twos in sample is 50%. Please, there's no formula here for what you'd expect. It would be crazy to expect anything else. So this has no formula. But the standard error, what's that? So to figure out the standard error, we're going to have to figure out the standard deviation of that box and use our formula. So the standard error for the sample percent, for this percent of twos in your sample, the sample percent, is equal to the standard deviation of the box, which you can call sigma, over the square root of n. Now that's just because an average right here. So you'll get a decimal as your standard error. But if you want to change it to a percent, you just multiply it by 100. Okay? So we can do that. So what is the standard deviation of that box? What is that? Well, do you remember the shortcut formula? Do you remember what that would be from last time? Here, you have a box that has 0 and 1. And let's say it has 50% of this and 50% here, like that one does. All right? So your standard deviation of this box, the average is a half, isn't it? Isn't the average a half? Right? And 1 deviates by a half, by 0.5 by 0.5. It's 0.5 above. That's your your plus deviation. And 0 deviates by 0.5 below. So you have 2 deviations that are both one's positive 0.5 and one's negative 0.5. So your typical deviation has to be 0.5 because those are the only deviations you have. Your average is a half, and you have your average. If you average these, a half, and these. So it's pretty obvious. But if you want to do it, you would say the numbers on the tickets, 1 minus 0, that's the distance here, times the square root. You could either say the fraction that have 1s, which would be 2 over 4, times 2, the fraction that have 0s, 2 over 4, or it doesn't really matter how many tickets are in there. You have 50%, so you can write the fraction as a decimal. 50 and 50, right? So that's the fraction of 1s, and that's the fraction of 0s. And that's the square root of 0.25, and you know the square root of 25 is 5. So this is 0.5. 0.5. What if you had, just as another example, let's just do another example. Let's say you had a 0 and 1. Let's say you had an 80%, 20% split. And it doesn't matter which is 80 and which is 20. Then you'd have what? 1 minus 0. Do we really have to write 1 minus 0? That's 1. You'd have you'd have 0.8, right? The fraction that are one of the numbers, times 0.2, and that's the square root of 0.16. What's the square root of 16? 4. So this is 0.4. This is the biggest it can be if you just have 0s and 1. The largest your standard, because you have the most uncertainty. You don't know if you're going to get a 0 or 1. Here you're pretty sure you're going to get a 0. So it's going to range, this is the largest. I think you have a homework problem like this. This is the largest the standard deviation of a 0, 1 box can be. And what do you think the smallest the standard deviation of a 0, 1 box can be? It's going to keep going down, right? Until what? Until you have what? All 1s or 0s. It doesn't matter which way you do it. You could say all 1s or all 0s. You could say 100% here and 0%. Well, then it's going to be 0 times 1, which is the square root of that. And you know it is because, and that's the smallest it could be because there's no variability. You know that all the numbers are the same, so the standard deviation is 0. So if you're figuring out the standard deviation of a box that just has 2 types of tickets, make sure your number is between 0 and 0.5. Otherwise, you've made a mistake. All right? So let's do this. So now, So now we have 30, so now we're going to do this. Okay, so we have 0.5, and it's over the square root of what? We have n is 36, right there. So and that is 8.33%. So I just wanted to go over that so you, whenever you see a problem where you're trying to find the standard error of a percent, you know this numerator here has to be between 0 and 0.5, and then you're just going to divide by the square root of n. And you can probably estimate it in your head. Okay? So now, let's think what else we need to know. So basically, these expected value formulas, there is none except for the expected value of the sum. So this is the only one that you need to remember. That's it. You don't need formulas for the expected value of the average or the percent because it's just common sense. You'd expect the average of the draws to be the same as the average inside the box. Let's highlight this. So that don't even overthink this. If you just do it before you had a statistics class, you'd know this. And you'd expect the percent of ones in the draws in your sample to be the same as the percent of ones in the box. In other words, you'd expect the draws to mirror the box and have the same average or percent as the box. So you only have this one formula for as your statistic for the expected value of the sum. So it's only for the sum that you need to, and there you multiply by n. But you do have these three formulas. You can think of them as formulas, but they're super easy. For the standard error, sampling error. Think of it as sampling error or standard error of your sample. Okay, you'd expect, here's what you'd expect your sum to look like, and your average and your percent, and how much variation around it is there. So think of it this way. You have okay, so for all of these, for the sum, all these standard errors, just write, they're all standard deviations. So they're standard deviations of the population, right? But they depend on n. And they depend on n by the square root law. So you either, for all of these, you either multiply or divide by the square root of n. And the only one you multiply by the square root of n is for the sum. So let's just do that one. So the sum, you multiply by the square root of n. Because sum gets bigger and bigger and bigger, right? So think you multiply. And for these two you divide. So for an average, you divide. For both of these, you divide. Okay? So let's make that. So that's really all you have to remember. It's not really, because I don't want to give you formulas that don't make sense. And this is all you need to remember for these formulas is either you multiply or divide. And that's why I think it's really useful. I'm warning you now, you're not going to get these formulas on the exam. So I just want you to think of it logically. Yeah, do you have a question back there? No, just stretching? Okay, so for these you divide by square root of n. Okay, and then just for the percent, like like 0.5 is 50%, right? You just want to change it to a percent. So you have to multiply by 100. That's because it's a percent. So that's the idea of that chapter. Any questions? It's probably really easy for you to remember that, but again, this was the summary. Always read these summaries. They're extremely useful. It started here. All right. And now what are we going to do? All right, so now, this is probably a little more interesting. Now we're going to look at probability histograms and something called the central limit theorem. Now remember, just in chapter 5, we used the normal curve to approximate, to figure out chances for data sets that approximately followed the normal curve. And we did that by changing to a z-score. And it was super useful. But I said this normal curve is going to be unbelievably useful. And that's because, and this is sort of magical to me, that's because it's the probability distribution, it's the histogram for taking, like, if you took n draws from a box and either took the sum, the average, or the percent, the distribution of all those possibilities around is going to follow the normal curve. So you know what the expected value is, you know what the standard error is now, but the beauty of it is no matter what numbers you have, I don't care what your box looks like, what your population looks like, the central limit theorem, which we're going to look at, says that if you have enough draws, that the probability distribution of all the possible sums, or all the possible averages, or all the possible percents you could get in n draws from a box is going to resemble the normal curve. It's really shockingly gorgeous. And so I'll show you that, I mean, amazingly so, in a minute. I mean, it's a hard proof, but I think you'll get an intuitive feel for it. But first, I really want you to understand this. I want you to draw a probability histogram so you'll get a feel for it first. Okay? So let's just read along here. So it says, in previous chapters, we summarized lists of numbers. Just the numbers you had, not a chance process, just I gave you a list of numbers, by the average and the standard deviation. And then we graphically displayed them with a histogram. Okay? Now we're doing the same thing with numbers, with something called random variables, numbers generated by a chance process. We summarize the average and the standard deviation of variables drawn by a chance process, by the expected value and the standard error. We also did the sum. Now we'll draw a histogram to describe all the possible outcomes we could get and the chance of each outcome. That's called a probability histogram. It's very much like the histograms we had for a list of numbers. The only difference is instead on the y-axis, I'll show you. So instead of having all the numbers on our list, we're going to have on this x-axis all the possible outcomes from our chance process. And instead of having on this axis the density or the frequency of each of the numbers on our list, we're going to have the probability of each possible outcome. So it's going to look really, really the same. Okay? And now this gorgeous central limit theorem, which is one of the most important theorems in all of statistics, it says the probability histogram of all possible sums, or averages or percents, because they come right from sums, you just divide by n to get them, of draws from a box will get closer and closer to the normal curve as the number of draws increases. Note this only applies to sums, or averages or percents. For example, if you took two numbers out of here and multiplied them, it wouldn't apply to products, or just to the sums, averages, and percents. Okay? So now let's look at this. And so what I want to do is, let's say you have the box model for flipping a coin and counting the number of heads. And we're going to see, like, in one toss, it's not going to look so much like the normal curve, the probability histogram. Then we'll look at 2 tosses, 3 tosses, and 4 tosses. And by then you'll get a good feel for why it's going to start looking like the normal curve very quickly. All right? So let's think about what this means. So to draw the probability histogram, you have to think of all the possible outcomes, because that's going to, like for n equals 1, that's going to be here, all the possible outcomes. So what could you get? You could get you could get one tail, which would be 0. We either have 0 heads or 1 head. Those are we have 2 possibilities with just n equals 1, right? You draw from here, you either get a 0 or a 1. So what does that look like? So here 0 or 1, those are only 2 possibilities. And then we can just draw this and just, I don't draw this axis and just say, okay, there's a half a chance that you get a 0 and a half a chance you get a 1, 0.5 or a half. That would be the probability histogram for either, you can call it the contents of the box or one draw from that box. Do you see? It tells you the possible outcomes and tells you the chance of each. That doesn't look like the normal curve yet, right? So now, what if you draw again? What if you do again? So now what? Now there's, you could either get the tail, and then there's two more possibilities from here, or the head, and there's two more possibilities. So you could think of it as, okay, on draw 1, we got 0 or 1, and now let's look at our second draw. We could either get, what, a tail or a head. So we could get a tail or a head on our first draw, and we could get a tail or a head on our second draw. And so if we summed them up, if we got two tails, it would be 0 heads plus 0 heads is 0. If we got 1 head plus 0, could look like that. Or 0 and 1, or 1 and 1 is 2. So on two tosses, we knew that you can get, we already knew with two tosses, there's three possible outcomes. There's 0, 1, or 2. But we didn't know the likelihood of each. We didn't know. Now you can see, you can get, there's two ways to get one head. You could get here, here you got a hail and a Ted. Hail and a Ted, right? A head and a tail. And here you got a tail and a head. So how are we going to draw this? Well, there's 4 possibilities, so only one way to get a 0. So that's 1 out of the 4 would be a quarter. So this would just be a quarter high. And this would be a quarter high. And this would be, there's 2 ways. So it's going to be 50% of the time. 2 out of the 4. So that's what it would look like. And so right here would be a half, and right here would be 1/4. Can you see that it already looks more like the normal curve than that one? Can you? So how, do you want to keep going? Should we do it? Nod if you want to see more. You got to nod. If you want to see more, you want me to go on. Go on, or you want to see more? Some people want to see more. So let's do the next one. So now you put, okay, so now after 2, we have 4, we had these, this was our possibilities, 0 heads, 1, 1, and 2. So now we're going to have, each time you can see, okay, so now you can see how we're going to double that. This is where the 2 times 2 times 2 comes, right? Now we're going to have 8 possibilities, because now in our next one, you could either get a tail or a head. And if you get a tail, that's not going to change the number of heads, right? So we can just write this down again. But if we get a head, it's going to add 1 more to each of these, right? So we're going to get 1, 2, 2, and 3. So on 3 flips, you already knew it was going to be, the possible outcomes are 1, 0, 1, 2, and 3. You already knew that, but you didn't, now you can see the chances of each. All right, so the chances of each are what? Well, there's one way to get a 0 and a 3, and there's 8 possibilities. So 1/8 of the time, you're going to get a 0 or a 3. That's 1/8. Now, how many ways? There's 1, 2, 3, and 1, 2, 3. Okay, so now 3 times as high, you're going to get either a 1 or a 2. Now, that doesn't look beautiful there, but that's going to go up to what? 3/8. It's 3 times as high as the 1/8. And so that's your, does that make sense? Okay, so now let's say we have 4 tosses. And so how many possibilities are there? There's going to be 16. We have the 8 that we did before, so let's write those down. 0, 1, 1, 1, 2, 2, 2, and 3 heads. And now we're going to toss the coin another time. And if we get, you either get tails, in which case it's exactly the same number of heads as we had before, or we get a head, in which case we add 1 more head. So this is 1, 2, 2, 2, 3, 3, 3, and 4. So again, we've doubled our possibilities, and now we have 2 to the 4th.
And so let's draw the histogram. So on 4 tosses, we could get 0 heads, 1 head, 2 heads, 3 heads, or 4 heads. And there's only one way, one out of the 16 possibilities, to get a 0 and a 4. So that's going to be here and here. That's 1 out of 16. And then there's 1, 2, 3, 4 ways to get a 1, and 1, 2, 3, 4 ways to get a 3. So we'll make this 4 times as high, and this one 4 times as high. So that's 4 out of 16. And now there's 6 ways to get a 2. So this will be 6 out of 16. And now you can see this is looking more like the normal curve. Now, another way to get these probabilities, to get how many 2s, how many, like 6 2s, 4 3s, etc., is by using this formula for counting k heads out of n tosses. In n tosses, we can use this formula. N factorial, that's the number of tosses, divided by k factorial times n minus k factorial. So for example, if we wanted to check that it's right, these 6 2s, we could, example, let's use this formula and make sure that we get 6 like we did here when we listed them. So that would be 4 tosses and counting 2 heads. That's read 4 choose 2. How many ways are there to get 2 in 4 tosses? So that would be 4 factorial, which is 4 times 3 times 2 times 1, divided by 2 factorial, 2 times 1 times 2 times 1. And does that equals 12 over 2, which is 6. So it checks. So this is called a binomial coefficient, and it gives you the probabilities for each of the possible outcomes. How many possible ways you can get each one of them. And then you get the probability if you divide by the total number of ways. Like 6 out of 16 is the probability of getting a 2 on 4 tosses. And when you draw this histogram, it's called a binomial distribution. So this is going to come up again in a few pages, and you don't need to, you won't be tested on this. I didn't really explain how we got this. I know many of you have seen this before, but it's useful to know, and it will be useful to look at in the context of how these are exact probability distributions, how they compare to the normal approximation. And we'll do that in a few pages towards the end of the hour. Okay, so the central lesson here is the central limit theorem, and it says as the number of tosses increases, do the histograms look more and more like the normal curve? Yes, they do. And what's really cool about this is that it's not just for this particular example. It doesn't matter what numbers are in the box. Any numbers at all that you put in there, it doesn't make any difference. Eventually, with enough tosses, the probability histogram for these sums and also averages and percents will resemble the normal curve. Okay.
And you can see, if we go to the data program right here, you'll get, this is what our data program looks like, and you click on simulations, and we can look at these probability histograms of sums, and you can create what we just did. So we can create a box that just has 2 tickets, and then we can look at the sums. And here's the first one we did, We said 0 or 1. And here's like, this is for 100 draws, so it's 50% chance of each. Okay? And now you can look at, this is what it looked like for 2 draws with a 25%, 25%, and 50% chance. This is what it looked like for 3 draws, and this is what it looked like for 4 draws. Right? So I think we did that. Now, watch what happens, though. If you keep going, it's going to look more and more like the normal curve. See how beautiful that is? So if we did 100 draws, see, 50's in the middle, and we'd have a standard deviation of 0.5 over the square root. I mean, this is for sums. So it'd be 0.5 times the square root of 100, which would be 5. Square root of n times the standard deviation. Now, the thing is, though, what if we had a really lopsided box? Like, let's say we added something else here and made it more lopsided. So let's say we added 100. Okay? So now what would it look like? You can't even, look how lopsided it looks like. But do you think it's going to get normal? Yes. With more draws, it's just going to take longer. It's so amazing. I mean, it really doesn't matter what you start off with. Like, you could have a crazy box. You could have, like, oh, I don't know, anything you want. You can play with this, and you'll see it's going to take longer the crazier and more abnormal it is. But I think this is a breathtaking theorem. That's the central limit theorem. So now let's go back to the document camera. Do you have any questions on that? It's really pretty gorgeous. So now we'll just illustrate it with these 2 boxes. One looks more normal than the other. So we'll draw the histogram for the contents of the box, right? Well, there's one possibilities with just one draw from the box, or the contents of the box is just 1, 2, and 3. And they all have equal probability of 1/3. How about this box? This, now you have to draw all the possible outcomes here, but you have to draw them to scale. So you draw 1, 2. There's no 3 through 8, but you can't go 1 to 9. You have to remember this axis. This is a regular histogram where the area adds up to 1, and this has to be drawn to scale. So we'll do 3, 4, 5, 6, 7, 8, and 9. And so now they each have 1/3 possibility of happening. So this is going to look like this. And then, but you can't, there's this huge gap, and then there's a 9. So this is like, what's the question? Which differs more from the normal curve? This one differs more from the normal curve. Box B. Why? Because it's so uneven. I mean, it's so uneven compared. This is a uniform distribution. It's uniform all the way across, so it looks more closer to the normal curve. The normal curve doesn't have this huge gap like that. So it's so uneven, so it will need more draws, the sum of more draws, or the average of more draws. So more draws are needed before it reaches normality, before the curve looks normal. Does that make sense to everybody? So why don't we just do it for these 2? And so you can see that. So if you did it here, okay, so this is your first draw, like we said before. And this is your second draw. And we can just, we can add them up. So you'll get 2, 3, and 4 when you add 1 to each of these. And you'll get 3, 4, and 5 if you have 2 to each of these. And if you add 3 to these, you'll get 4, 5, and 6. So those are your possible outcomes here. So you can, here they are, and there's 9 possibilities. 3 times 3 equals 9. So there's 9 possible outcomes. And well, there's 9 possibilities, but some of they repeat, right? So there's only these 6. Can you get a 1? No. Can you get a 2? Yes. So there's one way to get a 2 and one way to get a 6. 2 of those, 2 3s, 2 5s, and 3 4s. Okay, so this was out of the 9. There's just 1 out of the 9. That's 1/9 to get the 2 and to get the 6. So you could draw it like that. And then there's 2/9 to get the 3. It'll just be twice as high. To get the 3 and the 5 is 2/9. And then 3/9, 1/3 of the time you'll get the 4. So that looks pretty normal. 3/9. All right, whereas this one's not going to look normal. You can see that pretty well. This is going to be a 2, a 3, and a 10. And then you'll have a 3, a 4, and an 11. And now what do you have? 9 and 1 is 10, 11, and then 18. So it doesn't look anything like, once you draw it, it's not going to look, you still have 9 possibilities here. 9 possibilities. So let's look at them. Can't get a 1, but there's one, what is it? Out of the 9, there's one way to get a 2. There's one way to get a, 4? And there's one way to get an 18, right? 2, 4, and 18. Then there's 2 ways to get a 3, 2 ways to get an 11, 2 ways to get a, okay, so 2 ways to get a 3. So this is 1/9, this is 2/9, and then there's 2 ways to get a 10 and 11. So it looks like that. Now they're all going to add up to, they add up to 100%, the same way as our regular histogram. Any questions on that? But this, should we do it? Let's just make sure we did it right. Do you want to do it, or do you want to bother to go back to the computer or not and look at it? You don't need to? All right, well, here I copied down. Now look at the probability histograms, the sum of 25 and 50 draws, okay, from each of these boxes, and that's what's here. All right, and you can see that from box B, it's much more jagged, but eventually it gets more and more normal. This one has a bigger standard deviation. Do you see what these standard errors are? They're going to be square root of n times the standard deviation. The standard deviation of this box is 3.56. I looked on, by doing it, I don't know that offhand, obviously. But now if you do this, if you have 50 draws, notice how this standard error is going to be the square root of 50 times that. And this will be the square root of 25, 5 times that. And here, the standard deviation is much smaller. They're closer together, and the standard deviation here is 0.8165. So the standard error here is the square root n. It's going to be, this is equal to the square root of 50 times that one. And the expected value, of course, is equal to n times the average of the box. So the expected value is 50 here. See? That's n, 25, times the average of the box is 2. So you can just see how that works. All right. So any questions on any of that? All right. The expected value is right in the middle here, you can see. So now we're going to use the central limit theorem just the same way before. So instead of saying z equals the value minus the average over the standard error, now we have the same formula but instead of the average and standard deviation, we have the expected value and the standard error. So this is our z-score formula for random variables. It's the same thing. The expected value replaces the average, and the standard error replaces the standard deviation. So we can do an example here, and we can use this as long as we have enough draws, so that the histogram looks normal. So in 100 coin tosses, what's the chance of getting between 40 to 60% heads? Well, remember in two tosses, there's 2 squared, and 3 tosses 2 cubed, 4 tosses 2 to the 4th. At 100, there's 2 to the 100th possible ways, which is just, even if we wrote all those down, which would, if all of you wrote those down, 100, like head, 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 tail, 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 for 100 of those, you could get all heads, you could get all tails, and you wrote, let's say, 100 possibilities on each page, and then you stacked them up, it would reach from here to the farthest star. So you can't, that's impossible. I mean, if we all did that, it would be many, the Earth would be wouldn't last long enough. It just wouldn't for us all to accomplish that. So, but that's a huge number. All right, so there's no way we're going to list that, but we know that it's going to look really close to the normal curve, and so we can figure probabilities. We don't have to list all the possible outcomes because that would be impossible. Okay, so, so draw box models for tossing a fair coin. So we'll do that. And remember, you always draw the box for a single. All right, it's really simple. You draw for a single toss, and there's just 2 tickets. You either get ahead or you don't. Okay, and you can think of it as, I mean, you could have put 100 tickets. You can put however many tickets you want in here. Just remember, 2 is nice because you'll remember it's with replacement. Even if you had thousands of tickets, you still want to keep those chances 50-50. Okay, so then you draw from here 100 times because n is 100. Draw 100 times with replacement. And then take the sum of the 100 draws. Okay, so the expected value in the expected value for the percent in the sample of 100 is what? It's 50%. Because it's the same as the box. You know that. There's no formula for it. You just look here. All right? And the standard error for the percent in the sample is what? Now, here you do have to have a formula. It's standard. How are you going to remember this? Standard error, standard deviation. Just write it down. Those are the same type of thing. But this, because it's a chance process, depends on the number of draws. And by the square root law, you have to put the square root, either multiply or divide by the square root. So write down what you think you should do. Multiply or divide, so you'll remember, by the square root of n. It's like an average, a percent and an average, so you divide by the square root of n. Okay? That's the standard deviation of this. You could call it sigma, but I just want you to get this really clear and use. Okay? And then you have to multiply, because it's a percent, you multiply by 100. That's where that part comes in. All right, now I don't think we have to do this again. 50-50 box, you know, it's 0.5 and 0.5 what? It has to be 0.5. That's the biggest uncertainty you're ever going to get. You don't know if you're going to get a 1 or 0. The biggest it can be is 0.5. We're just going to put that down. All right? And now it's over 100, square root of 100. And if we did that, you get 0.05. But we multiply by 100, and that gives us 5%. All right? Okay. Now, do you want me? I can just write that if you want to see it. The standard deviation is the square root of 0.5 times 0.5 for that. All right. Now we want to convert these to a z-score. We're just going to use this formula. right? So for 40%, what is it? So z, I'll just write it right here. Z is going to be our value, which is either 40 or 60, minus our expected value, always over our standard error. And since we're talking about percents, it's going to be for our sample percent, right? So here's what we're going to do. The idea is this. We have our normal curve here, and we know that we have 100 tosses. So if we drew that little jagged probability histogram, it would look very, very much like this. But it would be a little discrete instead of a continuous distribution. It would have little jagged rectangles. Okay? And we know right in the middle is going to be what? 50%. 50 is a sum, but 50%. And now what do we want? We want to know where is 40 and 60. Okay? Where do we put it? That's all we're talking about. So for 40%, the z for 40% is going to be what? Our value is 40, so we say 40 minus 50 over our standard error. So what is our standard error? We just figured it out. It's right here. So it's over 5. So that's -2. Why? Because we just saw our standard error is 5%. So that means that one standard error is 5%. So this would be 55. This would be 60. In terms of percent, this is in terms of a z. We have another axis, right? So we'd go down to 45%, and this would go down to 40%. So we can see it's going to be -2. So that's right there where 40 is. And obviously 60 is going to be there at +2. You know, z for 60 is just 10 above. The standard deviation, standard error is 5, and we have 10 of them. So we have 2 standard errors above. So this is approximately, we wanted this area between is 95%. We don't have to, 95.45, but approximately 95% is our answer. All right. Now, any questions on that? All right. This is more of the same. Why don't we just do, we don't have to do all of these. So, okay, 36 draws are made at random with replacement from this box, has 4 tickets. So you always have to figure out the average of the standard deviation of the box. The average of this box is 12 divided by 4 is 3. And the standard deviation, I figured out before, it's also 3. All right? So this is the only one that has a formula. Do you remember this? First of all, you have to see how many, just remember, you have to look here. Because this is going to be n times the average of the box, right? So the expected value for a sample sum is n times the average of the box. So what do we get here then? We get 36 times 3. So that's 108. And our standard error for the sum of 36 draws. Okay, standard error is like the standard deviation. We know that. Now, are you going to multiply or divide by the square root of n? It's a sum, so you are going to multiply by the square root of n. All right, so we get 3 times the square root of 36. So that's 18. All right? So then, what's the probability that the sum of 36 draws would be greater than 120? All right, greater than 120. So here, 0, 1, 2, 3 is a z-score. And that's as a z-score, but another axis as a sum, right in the middle is going to be 108, and we want to know where to place 120 on. No, 108, and our value is 120. So it's 12 above. So we want to know, well, you could probably see. 12 above is just what? 2/3 of a standard deviation. So let's do it. So z equals, you know, it's going to be our value minus our expected value. These are sums over our standard error for the sum. And we said we had 120 minus 108. So that's 12 above. And we just want to know how many of the, it's not even one standard error, so it's not even going to reach to 1. Okay? It's 0.667. It's 2/3, right? So we have to go 2/3. So let's see what that middle area is. And 0.67. All right, so it's kind of in between 48 and 51 point. Let's just estimate. You can 0.667 at 2/3. Why don't we just say about 50%? Okay, in the middle. Does that make sense to everybody? It's going to be bigger than that one and smaller than that one, right? We can look it up exactly if you want, but let's just do it for now as, so 120 between z equals 0.67 and z equals negative 0.67. We have about 50%. All right, so we have about 50% in there. And the question asks us, this is just people make this mistake all the time, just which part of the curve do you want? You want greater, so just make sure you just shade that in so you don't forget. Okay, so it's going to be what? 25%. All right, that's your answer. And the average, and the, you know what, how about we skip these for now because they're going to be, and these will be ones that we'll do on your own. All right, and by the way, I posted the notes for the do on your own on the calendar, okay? So if you go here, we're going to go to the document camera in a minute, and to the PC in a minute. So you're going to do these on your own on page 57. Now, where I post these is I post them in the lecture, like this is lecture 6 today, so it will be right under in the calendar. And you can see the ones that, they're already posted, all the ones that we've skipped. So just look at the calendar and you'll see these are the skipped pages and you can fill them in. Because I want you to do these on your own, and now I want to get to something a little bit new. Okay. So, in some cases, this is on page 58, like the next two examples, it's necessary to make the normal approximation more exact by moving the endpoints of an interval to the nearest half integer, and that's called making this continuity correction. Why? You'll see why in a minute. In 100 coin tosses, what's the probability of getting exactly 50 heads, right? So exactly 50 heads. So as a z-score, you have 0, 1, 2, 3, -1, -2, and -3. But we want exactly 50 heads. So if we were doing our, if we were going to do the normal approximation, we'd have to get the expected value, right? And that's going to be 50 for the sum. It's n times the average of the box. Your box is just 1 and 0, right? So your average and your standard deviation is both 0.5. All right? So this would just be 100 n times 0.5. And it's 50. You knew that anyway. We have 100 coin tosses. So now, what's the standard error of the sum going to be? The standard error of the sum is going to be this. It's a standard deviation, so that will be 0.5. And then you're going to multiply it by what? The square root of n. So that's times the square root of 100. So you get 5. Right? All right. So now, if we do that, so now you think, look what happens if we do this and we say, okay, now we're going to get a z-score. And what is our value? Our value is 50, but the endpoints of the interval are both 50. So there's no, it's exactly 50, right? So our z-score would be 0. We can say the value is value minus expected value over standard error. And we get 50 minus 50 over 5, which is 0. And we don't have any interval. So how are we going to figure out any area? And this would be true for exactly any number, not just 50. You have an interval of 1. So what are we going to do? It's not 0. For a continuous distribution, you know, the intervals get smaller and smaller, and you're going to have an area of 0 no matter what you choose. So what we do is we try to create an interval of 1. So we go down to, the interval becomes, instead of 50, we make an interval on this axis here that goes to 49.5 and to 50.5. So that's the nearest half interval in each direction. Now you have a width of 1, okay? So basically we're trying to find the height of the curve right there at the top. We have a width of 1. So let's see how this works out. So then we get our value is 50.5 minus 50 over 5, right? So that's 0.5 over 5, which is 0.1. That's our z. So we have an interval right here that matches up of z equals 0.1. And what do you think negative 49.5 is going to be? I mean 49.5, it's going to be negative 0.1, right? So that's z for 50, and z for 50.5, and z for 49.5 is going to be 49.5 minus 50 over 5. So that's negative 0.1, negative 0.1, sorry. All right, so we've got those two, right? So now we could look it up on the normal curve between 1.1 and 1, and what do we get? We get 7.97%, about 8%. 7.97, about 8%. Now there's another way we could do it. And we could use this binomial coefficient. Let's see if we come up with the same thing. So the other way we could do it would be what? We would be using this binomial. Out of the two, there's 2 to the 100th ways it could fall. How many of them, this binomial coefficient right here, would be, remember it's n choose k. So what we want is 100 choose 50. So that would be 100 factorial over k factorial times n minus k factorial. It's 100. Right here we have 100 choose 50 over 2 to the 100th. That's what we're doing. So now we can do that on the computer, and let's see if we get the same thing. By the way, you don't need to know this. This is just for your own, you don't need to memorize this. I'm just showing you how cool it is to be able to use the normal approximation, because this is a huge number. So let's go to the computer and see if we can calculate that number. Let's see. What if we just put in the number? So we'll say 100 factorial divided by, what are we going to divide it by? 50 factorial, 50 factorial times 50 factorial, and then we'll divide that by 2 raised to the 100th. Let's see what we get. See, we get 0.0795. So remember that. Let's just get, our chart gave us something very close. Let's look at that. And then we can also go to our p-value calculator and do this and see if you want to look for more exact ones. We could say, okay, we want a p-value of 0. We have a z-score of 0.1, and we want to compute the middle area, and there we have the same thing, 0.07966. So this does an extremely good, the normal curve does a very, very good approximation. This is the exact probability. This is the exact probability when you calculate this. And the normal curve gives something there. I just want to show you how good the approximation is. You see, it's still an approximation, you know, but when we know exactly what's in the population, we can do a probability histogram and figure out through math the exact probabilities for each one. So if you if you went 400 tosses, you could see how that would change. Okay, so where would it change? The 400 right here would double that, right? Square root of 400 would be, instead of 10 here, you'd have 20, so that would double that. So then we'd get, we'd be having that, so we'd have a 10 down here, so we'd have 0.05. So if we look that up, 0.05, watch. If you look that up, you can probably guess what it's going to be. It's just going to be, okay, 0.05. It's about 4. This is about 8, and this is about 4. Because right in the center there, it's like a rectangle. It's like there, so we're just cutting that in half. So, and then you could do, in 400 tosses, you'd have 400 factorial, right? Over, and you'd expect, in 400, you'd expect 200 heads. So you could try that, 400 factorial over 200 factorial, 200 factorial. Anyways, and you'd have 2 to the 400. And you'd get something really close. So I just want to show you this stuff because it's really extraordinary what the normal approximation can do. If we had to count all those and list them, the planet would never last long enough for us to do that. And that's the power of math and the power of statistics. It's just beautiful. So I just wanted you to appreciate it. And think about, here we are, just knowing this stuff that we can do, even though we could never possibly list the ways. I mean, that's how big a number 2 to the 100th is. So I just want you to be in awe of statistics, in awe of the normal curve, and in awe of what we can do these days with it. I mean, what you can do through learning about it. Okay? That's the end.